So the law of conservation of energy tells us that the energy of a system cannot be destroyed or created, that the total amount of energy will always remain the same. What we're going to look at in this video is how to apply that to mechanical situations and do some calculations to be able to predict unknown values using the conservation of energy. We'll start with this basic idea that's on the screen here, where we'll take a look at kinetic, gravitational, and elastic potential energy, remembering that at each location we need to ask these three questions. Is the object moving? Then it has kinetic energy. Is the object elevated above its lowest point? Then it has gravitational potential energy. And does the system have some sort of elastic material in it, like a spring, that can be stretched or compressed? Then we'd want to consider elastic potential energy. In this situation, we are trying to drop a ball from a certain height so that when it hits the ground, it's traveling just as fast as a Major League Baseball player could pitch it at 45 meters per second. So this is a change in vertical height, and so we should definitely be thinking about gravitational potential energy. But let's go through the steps here. We're going to start with our basic statement that the energy at one point equals the energy at another. And let's define what those points are. So we're going to have the top of the drop, and we're going to have when the ball reaches the ground. That's the type of information we're given in the problem, and so those are the two locations that we want to focus on. Again, the total amount would stay the same all the way through, but I don't have information about partway through the fall. I only have information at the top and the ground. So those are the two locations I'm going to compare. We want to consider all the different types of energy, and we can eliminate certain things as we go. For instance, at the top, we are dropping the baseball, which means it's not thrown or launched. It has no speed at that moment. So at the top, there would be no kinetic energy. But at the bottom, there certainly would be. I am told that the speed of the ball is the same as it would be if it were pitched. So the speed is 45 meters per second as it strikes the ground. Don't get confused and think, oh, well, it's going to come to a stop. Eventually it will, but we are interested in just comparing the moment it's dropped to the moment it hits the ground. Now, in terms of gravitational potential energy, the question is the object above its lowest point? And at the beginning, it certainly is. So we would keep that u sub g in our setup. But when it reaches its ground, when it reaches the ground, that is the lowest point. And so there would be no u sub g at the bottom. And now this problem has no mention whatsoever about elastic materials, springs, and so forth, so we would completely ignore that type of energy in our setup. So that leaves us with potential energy due to gravity, mgy, set equal to 1/2 mv squared. Now, these are amounts of energy at two different locations. It's very important that you keep that in mind. The two sides of the equation always represent two different positions, two different moments in the motion. We would plug in our values on the left using the given mass and our value for little g on Earth. Y is what we're going to be looking for, how high up the ball was dropped. And then we would include the kinetic energy ideas, mass, and the speed squared. You end up getting 101 meters, which is pretty high, probably about a 25 to 30 story building that you'd have to drop this ball from. Before we look at a conservation of energy question, let's just play a little bit with the new formula that was introduced relating to the elastic potential energy. So it depends on the amount of stretch and on this value called the spring constant. The spring constant tells you how many newtons of force are needed to stretch something a full meter. Okay, so that's what the 6 newtons per meter is, and that's a very low number, and so that corresponds to a rubber band being very stretchy, very easy to stretch. One more thing I need to think about though is this amount of stretch, which is the delta x. It's given to us in units that we would probably be measuring in, but not the units we need for a problem. So we're going to want to convert that to meters by dividing by 100, because there's 100 centimeters in 1 meter. Putting things into our formula then, we get, again, a very small amount of energy, 0.12 joules, which should make sense because we're just working with a rubber band. It's not very stretchy. There's not a lot of energy stored in it. Notice that the amount of energy is measured in joules, just like every other type of energy should be. So let's look at a question that does involve an elastic material, but also involves the law of conservation of energy. So here we have a dart gun, and you may or may not be familiar with this. It's a toy where you have this little plastic dart that you push into the toy, and when you pull the trigger, the dart is released because a spring is released. So as you push the dart in, a spring is compressed, and then the energy that's stored in that spring can be used in terms of the motion of the dart. So we're going to again think about the energy at two different points, two different locations within this motion. And there's a lot of different positions you could be looking at, but based on the type of information given about the spring initially being compressed, we are going to have our initial energy be when it is loaded. Not when it's first released, because I don't know that speed when it's first released. It's when everything's loaded and nothing has started moving yet. And then the other point that I know a lot about is this peak, where we know the height and we're looking for the speed. So we definitely need to include that within our setup so we can find that unknown. Again, we'll think through our types of energy, all the different forms and so forth. At the bottom, before we release the dart and the spring is all loaded, there would be no kinetic energy right then. Okay, the dart doesn't begin to move until the spring begins to decompress or uncompress. But at the peak, there definitely is kinetic energy. The dart would be moving as it's going across the sky, so we would have kinetic. At the bottom, we would not have potential energy, gravitational potential energy, because the dart gun is at its lowest point. But at the top, at that peak, there absolutely would be gravitational potential energy. There's a height 2.5 meters above the ground given to us. That's going to be used to determine that energy. In terms of the elastic energy, at the very beginning, the spring is compressed. So we're going to have energy stored in that spring. But once the dart is released, all of the energy is out of the spring. Okay, it's all been transferred. And so certainly by the time the dart has reached the very top, that spring contains no more energy. And so we would take it out of this main setup. Again, this step is really for our thinking. You don't necessarily have to write this down, but these are the sorts of questions you should be thinking as you set up your problem. This is really the main equation that's needed, that initially we have all elastic potential energy, and later we have a combination of kinetic and gravitational potential. Let's see what the numbers look like in the formula here. So this is my value of K sub S, the spring constant, 20 newtons per meter. The amount of compression was 12 centimeters, but notice that I've entered this as 0.12. That's because I need to have that distance in standard units of meters. I divided by 100. I also need to have my masses in standard units. So we haven't seen this a lot, but if it's given to us in grams, there are 1,000 grams in a kilogram. Feel free to write that down if you need to. So we needed to divide by 1,000 or move the decimal place over 3 spaces. So that's the 0.003 here and here. There's our gravitational constant of 10 newtons per kilogram on the Earth, and then the height that contributes to the gravitational potential energy. got to go through a fair amount of algebra. Make sure you ask for help if you need help with those steps. But you do end up with a speed of 6.8 meters per second. And notice we didn't need to know things like what angle it was being shot at and so forth. Energy allows us to answer questions that maybe we couldn't answer with other methods. All right, one last question. So here we have a golf ball being struck from an elevated plateau, meaning like the top of a hill. And that hill is 14 meters above the ground. That's the H that's shown in the diagram here. And what we find is that the ball reaches the ground with a speed of 26 meters per second. So down here at the ground, that's its speed. We are trying to determine what must have been the initial ball's speed. So let's think through our types of energy. We need to choose two locations within the problem that are related to the type of information given. And hopefully it seems obvious. We're going to compare the plateau to the ground. Okay, because that's the type of information I have and that I need. We'll think about our different types of energy and ask ourselves, for kinetic energy, is the ball moving at the plateau? Well, again, don't get too confused thinking, oh, well, they had to put it on a tee or maybe it was sitting on the ground at some point, so, and you start thinking there's no kinetic energy. There has to be kinetic energy at the start, otherwise the ball is not going to leave the plateau. Okay, this is not a case where we're just dropping it. It needs to be launched. Plus, they're asking us to find the initial speed. That also tells us there has to be kinetic energy at the beginning. Kinetic energy at the end, yes, okay, there's a speed at the ground of 26 meters per second. Again, don't be thinking about the fact that it'll hit the ground and stop or it'll bounce. Yes, afterwards. We're just talking about this little chapter of the story as the ball goes from the plateau to the ground. Now, at the plateau, there is going to be gravitational potential energy because the ball is above its lowest point. But at the ground, there's no potential energy. Okay, so that's our first thing we can cross off. But the other thing is that we can eliminate the elastic potential energy from this problem. There's no mention of springs or rubber bands. All right, so this is our basic idea, and notice I put some subscripts in here because I want to make sure I don't get confused and think that the V's are the same. This is the V that I started with, this is the V that I ended with. You could label them I and F if you wanted to, or plateau and ground. Just somehow you need to determine or indicate to yourself that those V's are different. All right, so it's time to start plugging in some numbers, but as I look, I'm not given the mass of this ball. So we might start thinking, how am I going to answer this question without that piece of information? But if you take a look at our setup, you should see that there's a mass, an M, in every single one of those terms. And it's the same mass, it's the mass of the ball. And so I could divide both sides of the equation by M and cancel those masses out. It does not matter what the mass of the ball was from an energy point of view. If I set up this sort of conservation statement, I can answer the question without knowing that mass. Now when we plug in our values, our 14 for the height, our 26 for the speed at the ground, we would end up with a speed of 19.8 meters per second.